Hello guys, good evening. Can you hear me?
Good evening, sir.
Good evening. Okay, so I think last class we have we had done with alcohol reactions, phenol reactions, correct? Okay, so we'll discuss with few reactions of ether. There are only few reactions left here. Most of the reactions we have already done. So few reactions we'll discuss for ether, and then we'll see carbene, the uh, intermediate, and the reaction which involves carbene intermediate. Okay. Okay, 2 more minutes. Let others also join, and then we'll start. Okay. So ethers, you see, um, ethers are what? These are the anhydrides of alcohols. Okay, ethers are regarded as anhydrides of alcohol, because alcohol reacts with each other and evolve water molecule, releases water molecule, and forms ether. Basically, the medium is acidic here. Okay, it converts into ROR and H2O goes out. Since water comes out, hence from alcohol and forms ether, hence ethers are the anhydride of alcohol, right? Few formula that you should know. Benzene ring, OCH3 attached, methyl phenyl ether. The name of IUPAC name is this, and the common name is, we call it as anisole. You must remember this. A very common solvent we have, 5-member ring with a oxygen present in the ring. This is THF, that is tetrahydrofuran. And one more molecular formula that you should know, it is methyl vinyl ether, because on the either side of the oxygen atom, we have methyl and vinyl present, right? So this one is methyl vinyl ether. Okay, the very small chapter. Most of the reactions we have already done. Okay, so we'll see only few reactions which we haven't done, and those reactions which we have done already, we'll just go through it once quickly. Okay, so write down all of you the method of preparation. Okay, preparation of ether. Preparation of ether. The first method is we can have dehydration of alcohol, right? Dehydration of alcohol. Okay, dehydration of alcohol, we have two methods in this, right? Two way we can do this reaction. The first reaction is acid catalyzed dehydration. Okay, acid catalyzed dehydration. Acid catalyzed dehydration is a dehydration reaction. H2O comes out in this reaction in presence of an acid. Okay, for example, you see this reaction we have done in reaction mechanism. If you remember, alcohol, we take 2 molecules of it, 2 molecules of alcohol, heated in presence of acid, conc H2SO4 you can take for this purpose, right? Concentrated H2SO4. And the temperature we use here is 140 degrees Celsius. Temperature is very important, right? And it converts into ROR. Ether and water comes out in this reaction. Okay. So if you remember this reaction we have done, and when you have temperature 170 degrees Celsius, this converts into what? This converts into an alkene. Okay. So it is temperature dependent reaction. When you take 1 alcohol of it, so at 170 degrees Celsius and above, right, it gives the product as alkene is the major product, and 140 it is an ether. And when the temperature falls in this range between 140 to 170, then the product would be a mixture of the two, that is alkene plus ether will get both product in this reaction. Okay, it is temperature dependent product. At higher temperature, elimination reaction favored, and it converts into an alkene. Right, so we have seen this reaction. So mechanism I am not discussing here. The simple one, SN2 mechanism, it follows. First it protonates one of the alcohol, and then other one behaves as a nucleophile, attack onto the alkyl group of the other alcohol. Okay, this is first method, acid catalyzed dehydration. Okay, the second method we have in this only, that is by catalytic dehydration. Means dehydration in presence of a catalyst by catalytic dehydration. Catalytic dehydration, like I said, as the name suggests, we use a catalyst for this reaction. Okay, so the catalyst we use here, mostly we use Al2O3, alumina, or we can also use thoria for this purpose, THO2, right? Thoria. Al2O3 is alumina. Okay, so in this what happens, you see, two molecules of alcohol is heated in presence of alumina around 250 degrees Celsius, converts into an ether, and H2O eliminates in this. One note you write down. If we take two different alcohols, if two different alcohol is present, then we get mixture of ethers. Okay, for example, R1OH plus R2OH heated with the same reagent converts into R1OR1 plus R2OR2 plus we get R1OR2. All possible ethers we get here. Okay. The next preparation method we have, the second one that we have already done, and the reaction is no. In acid catalyzed, we'll get if temperature is 140, we'll get one single this thing. Means all possible ethers we won't get. Either we get ROR or ROR dash, like that. Okay. Yeah. So the second one, the second reaction we have Williamson's synthesis. Okay, this reaction we have already done, and in the last chapter also, if you remember, we have done this reaction. So I'm I'm writing down the name here. Williamson synthesis. Okay, so this reaction follows SN1 or SN2 mechanism depending upon the alkyl group attached to the oxygen, ethereal oxygen, and it converts into an ether. Okay, so like for example, you see we have RONA plus R dash X. It forms NaX plus R dash OR. This is the reaction we have. Mechanism could be SN1 or SN2 depending upon the alkyl group present here, right? Now the another thing is this alkyl group, this R, this we won't take as benzene ring. Okay, because the in aryl halide the carbon halogen bond is difficult to break. This is the one thing you should keep in mind. Okay, but if you have any electron withdrawing group attached to the ring, then we can take this. Okay, the last chapter alcohol only we have discussed this thing. The same thing we have here. Okay, another reaction, the preparation method we have, that is alkyl halide with dry silver oxide. The third one, reaction of alkyl halide with dry silver oxide, that is Ag2O. This reaction also, it follows SN2 mechanism, and we have done this reaction mechanism, this particular reaction in reaction mechanism. Okay, so you can revise the mechanism over there. Here the reaction would be, if you take dry, it would be an ether. If you take moist, it would be an alcohol. Okay, so this reaction I have discussed already. The reaction is 2Rx plus Ag2O dry. Okay, if it is moist, you will get an alcohol. Okay, Ag2O dry, it gives, when you heat this, it gives ROR plus, we'll get 2AgX. This is the reaction we have, right? So with dry and moist, both we have done in reaction mechanism chapter. You can revise that. If it is moist, then Ag2O reacts with H2O and forms AgOH, right, silver hydroxide, which then reacts with alkyl halide and forms alcohol. Okay, so that is the reaction we have. One reaction that we haven't done is the fourth one you write down, reaction with alcohols with diazomethane. So the reaction of alcohol on diazomethane. Okay, so this reaction, it follows SN2 mechanism. SN2 mechanism, and the catalyst we use for this purpose, HbF4. Mostly we use HbF4, or we can also use BF3 for this purpose. Okay, so the reaction is, suppose we have an alcohol, that is ROH, reacts with CH2N2. CH2N2 is diazomethane. This is diazomethane in presence of HbF4. It converts into ROCH3 and N2 gas releases in this process. Okay, so we always, one side we always get methyl here, right? That's why we say this reaction always gives methoxy ether, right? This reaction always gives forms methoxy ether, because one side we have always CS3 present.
So, but can we take any other derivative, any other azide derivative,
Azide derivative,
like other than
like you
diazomethane,
say
any other alkyl
RCHN2.
group? Yes,
RCHN2, you're saying. Um,
yes,
RCHN2. Generally, we do not take, because diazomethane is this compound only. If you see, if you take RCHN2, the reaction is possible in that case also. But that reaction is not reaction with diazomethane, because the compound is not diazomethane. Diazomethane is this only.
yes.
With diazomethane, you'll get methyl ether, right? If you take RCHN2, reaction is possible. The product won't be a diazomethane, the methyl ether.
Okay.
Okay. So I have written here by mistake methoxy. It is methyl, not methoxy. Okay, it is methyl ether. This HBF4, what it does actually, it gives H plus to this CH3, CH2, N2 goes out from this CH3 plus, and then this nucleophile attacks onto this CH3, we get H plus goes out. Okay, so I'll just write down here, mechanism is not that important here. It's just with HBF4, it converts into CH3 plus and N2. Can write this way, plus N2 gas releases, and then here we have ROH, the alcohol. This alcohol attacks onto the, I have just written this step to make you understand. Okay, it happens in one single step only. So it is ROCH3 and H, and to stabilize this positive charge, H plus comes out, forms ROCH3. Right, and this H plus then combines with BF4 minus, forms HBF4. That is how the reaction proceeds. So diazomethane always gives methyl ether. Okay. Any fluorinating agent like BF, no, fluorinating agent we cannot use. It is not like it provides, it is giving fluorine into this. So fluorinating agent we cannot use, Anjali. Fluorinating agent are those which provides fluorine in the reaction. So that we use for fluorination purpose. Okay, fifth reaction I have discussed this reaction in alkene chapter. Probably you will recall this. Fifth one, the name of the reaction is alkoxymercuration. Alkoxymercuration, then demercuration reaction. Right? One reaction we have discussed in alkene chapter for the formation of alcohol. The chemical reaction of alkene we have discussed, which forms alcohol, and the reaction is oxymercuration demercuration reaction. Okay, so you see two different reagents. I am writing it down here. Reagent A, the first step we use HgOAc whole twice, then THF with some solvent, that is CH3OH, and the second step we are using NaBH4 and aqueous base H2O with OH minus. Aqueous base we are using here. This is reagent A. Reagent B is we use Hg OAC whole twice THF H2O, and then in the second step we use NaBH4 with H2O OH minus aqueous phase. Okay, this reaction here you see this reaction is this reagent. This reaction is alkoxy mercuration demercuration reaction. The difference in the two reaction is what? That we have here solvent is CS3OH with THF, and here we have H2O with THF. Okay, this reagent we use for oxymercuration and demercuration reaction. Okay, when we have H2O here, the name is oxymercuration demercuration. When we have CS3OH, it is alkoxy mercuration demercuration. Both reaction follows Markovnikov rule. Both reaction follows Markovnikov rule. What would be the reaction you see? Suppose we have an alkene, substituted alkene like this. This is reacting with the reagent A and with the reagent B. Then the product would be Markovnikov addition. Sorry. Here we have CS3 already present. Reagent A is CS3OH. So OCS3 get attached over here, and here we have H. Here the product is one CS3 is already present. Here we have OH and H. Right. So the source of this OCS3 is a solvent here. And what is a solvent? CS3OH. And that is why we are getting here OCS3. The source of this hydrogen is NaBH4. Source of this OH here is again the solvent, and the solvent is what? The solvent is water here, this water. And this H is NaBH4. Copy this down. So both follows Markovnikov rule. Finish.
One second.
Done.
Yes, sir.
Okay. The next reaction is the addition of alcohol to alkenes. Alcohol to alkenes. This reaction takes place in presence of an acid. Okay. What is the reaction? Suppose I'm taking a simplest alkene, double bond CH2, in presence reacts with an alcohol, in presence of an acid, mostly it is H2SO4 concentrated. It converts into CH3 CH2OR. Okay. The mechanism you see here, you can think of that this H plus attached onto this uh, hydroxy group, H2O leaves and it forms a carbocation. But at the same time, this H plus may get attacked onto this pi electron also. On the both place, it may react, correct? So it depends upon which one has better reactivity from the other, right? So the reactivity, the nucleophilicity of alkene is better than to that of an alcohol, right? That's why this H plus reacts reacts with this alkene first in the first step, right? H plus. So it converts into a carbocation which is CH3 CH2 positive charge on it. Okay. So this reaction involves the formation of carbocation. So first property is what? That carbocation forms and hence rearrangement also possible. Rearrangement possible. Okay. So when this carbocation we get this carbocation, then the alcohol behaves as the nucleophile in the next step, right? Nucleophile in the next step. So this is SN1 mechanism basically, right? Nucleophiles in the next step, this lone pair of alcohol, this attacks onto the positive charged carbon atom, okay? Converts into CH3, CH2, OR, H, and positive charge on this oxygen. Now in the last step, to maintain the concentration of acid, H plus comes out and stabilizes the oxygen atom. It converts into CH3, CH2OR. Okay, the reaction is not tough. Just you need to keep in mind that nucleophilicity of alkene is better than to that of an alcohol. That's why the reaction first takes place at the double bond. Generally, ether reaction takes place in acidic medium only. 2-3 points you can generalize for ethers. Basic medium it won't react because oxygen already has lone pair present on it, right? Which has basic property. So if basic medium is there, then there is no reactions of ether in general, right? So most of the reactions, or you can say all of the reactions of ether, takes place in acidic medium. Okay, one very important reaction of ether we have. This is the preparation we have done. Now, one very important reaction of ether, the reaction with HX. Preparation we have done 2-3 reactions of ether we have. Write down reactions of ether write down ether in general do not react in basic medium. Do not react in basic medium. Like for example, if I take this one, ROR, in presence of a base, OH minus, it gives no reaction in presence of a base because the lone pair already present onto this ether. Now the next one is in presence of H plus. It may give some product, right? It's like it forms an intermediate molecule, which is this, and then H attach onto this oxygen, and then it may give further product into this. So one general thing is what the reaction mainly takes place in acidic medium. Now in this you write down next the reaction with HX, hydrogen halide. For HX, the reactivity order is HI is most reactive because of the maximum bond length. Then we have HBr, and then we have HCl. Okay, depending upon the amount of ether or hydrogen halide, the reactions takes place here, right? Mainly the mechanism is SN2. Okay, so suppose we have the reaction R1OR2 reacts with HI, and we have a small amount of HI here. So it converts into R1I plus R2OH. R1I plus R2OH. If this HI you're taking in excess, HI excess, then it converts into R1I plus R2I, and H2O also eliminates into this. So we'll get here only alkyl halide, that is iodide, when excess of HI will take for this. Right. If one of the alkyl, one note you write down. That is, it's a general reaction. Okay. If you want to write R2I, you can write down R2I and R1OH. Here it does not make any sense, make any difference, right? But when we have different alkyl group present, then we'll see what is possible here. We'll do that. Okay. But anything you can write here. Okay. One note you write down. If one of the alkyl group is tertiary, then SN1 reaction favors. Then SN1 reaction favors. Okay. How this reaction proceeds, you see. General reaction first I'm writing down. Suppose we have R1OR2. And with HI, this H plus protonates this oxygen and it converts into R1OR2. Here we have hydrogen and positive charge on this oxygen. Then in the next step, depending upon this alkyl group, I am assuming SN2 here, right? But if it is tertiary, any one of the alkyl group, then the bond breaks, forms a carbocation first, right? So if it is tertiary, This I minus behaves as a nucleophile. It attacks onto this alkyl group, right? And this bond pair is taken up by this oxygen and goes out. So it forms R2I plus R1OH. So anywhere you can take. If this I minus attacks here, this bond breaks, right? You get the product like this.
Sir, can the R2I further react with HI to give alkane?
No, R1OH can react.
Oh.
R2I won't
Okay.
react. No, alkylite won't react with hydrogen iodide. And that is why if you take this HI in excess, right, in the next step, what happens? If HI is excess, then this R1OH reacts with HI according to the mechanism SN1 or SN2. H2O goes out and I attach with this. So it converts into Ri plus H2O. Clear?
But then in the previous chapter, when we had oxidation by reduction by red phosphorus and HI, then
Red phosphorus we do
and
not have.
the iodide also. Yes, sir, but the red phosphorus didn't have anything to do except to generate more HI. So if HI is already there in excess, then that can also produce.
Yeah, red phosphorus is converting I2. See, that reaction was different. There, I2 is converting into HI again, and that is reacting with the alcohol.
Sir, but HI is present in excess, no, sir.
Yes, here it is present in excess. Here we are taking it as an excess. See that it's not, we cannot compare two reactions there, right? Obviously, there are different conditions when you take red phosphorus and HI, and when you take only HI over here. Here, this HI is behaving as an acid. That's why it protonates this ether.
Okay, sir.
Right. So the condition is different. We won't discuss each and every aspect of any reaction. Right. We just discuss the basic thing that is required to understand the reaction. That's why in
Yes,
chemistry, in organic chemistry, you cannot compare like there it is happening this way, so why it is not happening here. Right, because there are many factors. We do not talk about the temperature there that we're using. Right, the reaction condition we are not talking about. We are just talking about this is a reactant and this is the reagent of the reaction. Other factors we don't discuss generally.
yes.
Okay, so this HI reaction, it gives you alcohol and halide. If HI is in excess, then alcohol further converts into alkyl iodide or alkyl halide, whatever it is, correct? So how it happens, the reaction may be SN1, SN2. This is not like I am telling you it is SN2. This is what I am taking here, the mechanism is SN2. Whether it is SN1 or SN2, it depends upon the alkyl group here, whether it is primary or tertiary, right? Primary or tertiary. If it is primary, then SN2, tertiary, then SN1. Here is one more condition. If you remember, we have discussed this reaction in reaction mechanism. If you remember this, I'll write down the reaction here. Suppose we have an ether, ROR, and this ether is reacting with HI in three different conditions. Here we have possible. One, two, and one more. We have three different conditions we have. The first one, when you have HI, but it is anhydrous. Second one, we have HI concentrated. Third one, we have HI excess. This reaction I have given you already in reaction mechanism. When HI anhydrous we have, then what would be the mechanism? Here what you have to keep in mind, if any alkyl group, this one or this one, is tertiary, because we have anhydrous, then only tertiary gives SN1 mechanism. If it is primary or secondary, then it gives SN2 mechanism. SN2 mechanism. And SN2 mechanism, the nucleophile is I minus. So I minus will attack onto the less hindered site, right? Less hindered site. That is the basic property of SN2 mechanism. Okay. If it is concentrated HI, then concentrated HI 2 degree or 3 degree gives SN1 reaction, and 1 degree gives SN2 reaction. If HI excess we have, then we get 2 molecules of Ri like we had in this reaction. So this is the overall reaction we have. I have done this reaction in reaction mechanism chapter. If HI is concentrated, right, then it gives a more amount of H plus and I minus, then it leads to the formation of carbocation easily. Okay, so these reactions are very competitive. You should know that what mechanism possible depending upon the ether that we have. One reaction you see, done all of you, this one? Tell me the product in this reaction. We have CH2 double bond CH. This is the ether we have, and this is allowed to react with HI. HI is not excess. What is the mechanism of this reaction?
So SN1.
SN1, why?
So because stable cation we found stabilized by resonance.
Yes, the mechanism is SN1, right? Because the right side you see, right side of the oxygen atom, the carbocation that forms on that, the next carbon of that oxygen on the right side, that carbocation is resonance stabilized. Okay, so this converts into, first of all, you see what happens. This H plus protonates this oxygen. Okay, the lone pair of this takes H plus from this HI, and this converts into CH2 double bond CH single bond O HCH2, sorry, CH2 single bond CH and double bond CH2. positive charge on this oxygen. Now you see, you can you can think of like either this or this bond dissociates, right? If this bond dissociates, you'll get a positive charge here, which is not at all stable because it is sp2 hybridized carbon atom, vinyl carbocation, right? This bond, if it breaks, this carbocation is resonance stabilized with this pi bond. That's why this oxygen, this will take this bond pair of electron and leaves out as the compound, which is this CH2 double bond CH OH. Just a second. OH, right? This forms, and we get a carbocation which is CH2 positive charge, single bond CH, double bond CH2, which the next step I minus attacks onto this carbocation and it converts into the allyl iodide. The product is CH2 double bond CH, CH single bond CH2I. This is the product we have. But this product is not the final product. After this, what happens? It goes under tautomerism and it converts into CH3 CH double bond. This is the final product in this reaction. So this part is more important here. Triad it forms, right? You see, 1, 2, 3. This hydrogen comes over here, and this pi shift onto this oxygen. We get a double bond. So it goes under tautomerism and forms this product, that is acetaldehyde. Important one, must keep that in mind. Is it SN1 because it can give stable carbocation? Since a stable carbocation is there when you have positive charge here, it can form a carbocation which is resonance stabilized. That's why it is SN1. Similarly, if you do it like CH2 CH3 double bond you remove, it is not SN1 then. It is SN. It is not SN1. It would be SN2 in that case. Okay. Fine. So this part is important. Okay, it is more important. It goes under tautomerism and forms this. Next reaction you see, hydrolysis of ether. Hydrolysis of ether takes place in presence of an acid H plus H2O. Right, generally we take dilute H2SO4 for this purpose, and it converts into an alcohol. Okay, alcohol. The reaction may be SN1 or SN2. Okay, depending upon these two allyl group, alkyl group, R1 and R2. So, for example, if R1 and R2, if R1 and R2 both are 1 degree, then it is SN2. SN2. If any one is secondary or tertiary, the reaction is SN1. Right? That is the only thing we have. If not 1 degree, then SN1. Tertiary goes under SN1, that we do not have any doubt in that. If you have secondary, then also the medium is polar protic. And you know, in polar protic solvent, SN1 reaction favors. Okay, how this particular information is important, you'll understand by this particular question. You see this, if the question is this: CH3CH2O CH3 and CH3. If this goes under acidic hydrolysis, H plus H2O, H plus H2O, and this is, suppose I am taking an isotope of this oxygen, this is O18, then what would be the product in this reaction? Tell me. And in this one also. This is also O18. Okay, so you see here, this H plus protonates the oxygen, ethyl oxygen. So if you try to understand this, the H plus comes over here, oxygen will get the positive charge, and since it is secondary carbon, this comes out here, and this carbocation forms here. Hence, the product of this would be CH3, CH2, OH. Here we have O18, and this converts into CH3, CH3 and OH here. Sometimes they'll give you D plus D2O, D plus H2O. In that, all those cases, this kind of information is important. Same thing here, what happens? This H plus comes over here. Then this bond won't break because this carbocation is not stable. Okay, so I've just written here to make you understand. Just remove this. Just a second. Okay, so similarly in this one, if you see, the product would be the O18 goes with the ring, benzene ring, right? This double bond would be as it is. Here we get OH18, and this carbon, here we get OH from the solvent, that is H2. Right? This is the product we get.
Sir,
Yeah.
sir, when the carbocation forms, won't it undergo hydride shift and
If
become?
possible, then it will go. If possible, then it will go.
Sir, here it is possible, sir.
Yeah, here it is possible. I will do that. Okay. That's what I was about to. So the point is, you'll get a carbocation here, right? And we'll get this product. But this would be what? This would be the minor product in this reaction. Right? This would be the minor product in this reaction. And then you will have all those hydride shift, methyl shift, and it converts into a major product, which is this OH18 would be as it is 1, 2, 3, and here we get OH. Yes. Done? Okay, the another reaction is halogenation. Halogenation of ether. Two more reactions we have in this, three more actually, and then we'll done with this chapter. The next reaction, write down halogenation. Halogenation of ether takes place in presence of light as well as in dark, and we get two different product here. I'll just write down this with this example. Suppose we have a molecule CH3 CH2 OCH2 CH3, right, in presence of light Cl2 in presence of light H nu. We'll take excess of chlorine, that is 10 Cl2 we are using, excess of chlorine, and all the hydrogen here is replaced by the chlorine. Product is CCl3 CCl2 OCCl2 CCl3 plus 10 HCl. All hydrogen get replaced here. But if the same reaction is taking place in the dark, in absence of light, Cl2 dark, then the reaction takes place only at the adjacent carbon, alpha hydrogen. Okay, that is CH3 CHCl OCH2 CH3 plus HCl. This is the product we get. Only at alpha carbon. It follows free radical mechanism. The free radical at adjacent carbon is quite stable because of this oxygen here, right? So this may form here, right? This may form, but at this carbon, the free radical is not stable and it won't form at all, right? That's why in dark, the reaction takes place only at alpha carbon, but in light, all the hydrogen get replaced by chlorine and forms HCl. So it's a factual reaction actually. Mechanism, they, it's not given anywhere. So you have to memorize this. In presence of light, all hydrogen get displaced, and in presence of, when in absence of light, only alpha carbon takes place in the reaction. No, we are taking only Cl2. If you take 2 Cl2 or 3 Cl2, the reaction takes place only at alpha carbon. But actually in dark, what happens? The dissociation of chlorine bond is not that easy. Here what happens? Light, we are providing energy, correct? Hence dissociation is possible for chlorine and the reaction is also easier. Yes, only alpha hydrogen. But in dark, the reaction is difficult, right? It takes place only over here. Okay, next reaction you see, we have reaction with base. Write down action of, yes.
So what about the other alpha hydrogen?
We have only one Cl2, no? So either this or this, the reaction takes place.
Okay.
We have only one Cl2. Suppose you have one more here, then takes place over here, Cl2. But only at alpha, not at the other carbon.
Okay.
Action of base, you see, like a strong base, if you are taking CH3 minus Li plus, okay, it gives you a different kind of product in this reaction. Like for example, suppose we have a base like Li plus and CH3 minus. In organometallic compound, the last reaction, last chapter, we have seen this Li plus, the S block elements, they behave as a stronger base here, right? So when it reacts with an ether, which is this HCH2 CH3 OCH2 CH3, then this base takes H plus ion here. It is an acid base kind of reaction. This R minus takes this H plus. This bond pair of electron, it leaves over here. and this moves out as the leaving group. Okay, so it converts into CH3 minus an H forms CH4, plus we get an alkene CH2 double bond CH2, and the leaving group, with the leaving group we have C2H5 O minus and Li plus will get neutralized like this. So in presence of a base, this kind of reaction is possible. I told you in the beginning that reaction with base of ether is not that easy, right? But when we have a compound like this, then it may take this kind of base, not that NaOH or KOH. This base R minus takes H plus and it forms the mixture of alkane and alkene. One last reaction we have in this, we have already done with Friedel-Crafts reaction, acylation, alkylation. Epoxide reaction we have already done, right? That is the cyclic ether. Epoxides are nothing but cyclic ether, right? But one last reaction in epoxide, we'll see how the reaction takes place in acidic medium and basic medium. Important, this reaction is important, okay? Epoxide reaction. So the last one you see, the reaction of epoxide. And I'm taking here unsymmetrical epoxide. Suppose the epoxide is this, and we have two methyl group present over here, right? The reaction takes place with an acid that is H plus solvent. Suppose I am taking CS3OH, acidic medium. Okay, this acidic medium, it protonates the ethereal oxygen, which is this. This oxygen takes this H plus and it converts into this one. Right. Acidic medium, the reaction first takes place at ethereal oxygen. And then what happens here? The ring opens up. So from which side it opens up, that you have to understand. The ring opens up in such a way that we get more stable carbocation. So this, from this side it opens up so that this carbocation is more stable than this one. So the product we get here is this OH positive charge on this. After this positive charge, the nucleophile is this CH3OH. So CH3OH behaves as a nucleophile. It attacks onto this carbocation and converts into OH, OCH3 finally. So you'll get an ether. So mechanism of the reaction is SN1 here. It forms a carbocation and SN1 reaction takes place. Okay, if the reaction is this acid catalyzed reaction, okay, epoxide with acid catalyzed. So what you have to keep in mind in the reaction of epoxide in presence of acid, the epoxide ring opens up from more hindered side. From this side it is getting open in order to get the more stable carbocation. Okay, if you have a base, for example, CS3O minus, since we have to form ether, that's why I'm taking this base here also. You see, we are getting ether here. In presence of a base, the reaction is SN2 here, and the ring opens up from the less hindered side because it is SN2. So this will always attack onto the less hindered side from the back side. Here we have more hindrance. This won't attack onto this carbon. It will attack over here, and this bond pair is taken up by this oxygen. So this converts into I'll write down other way so that it attacks from the back side. So we have OCH3 here, and here we have O minus because it takes this bond pair, and this O minus get protonates from the solvent, that is what we're using CH3OH. I did not write here, but the solvent is the conjugate acid of this, preferably we take, right? CH3OH. It protonates from this and it converts into OCH3 here, OH, and this is the product of this. So the two reaction, when the site is hindered and the mechanism is basic medium. So basic medium mechanism is SN2, right? The ring opens up from the less hindered side. Acidic medium mechanism is SN1, and the ring opens up from the less hindered, from the more hindered side, in order to get more stable carbocation. Okay, always remember acidic medium reaction starts with this ethynyl oxygen. Okay, this take part in the reaction and it proceeds this way. Okay, done.
Sir?
Yeah.
Sir, OCH3 and OH are like placed anti to each other or something?
Yes, yes. Always SN2 is always backside attack. Okay. This OCS3 will be from the back side and this is this side.
Okay, sir.
Okay. Done. Just a second. Okay. Fine. So the next, this is it for ether, right? So alcohol, phenol, ether we have done. There are some aromatic conditions like aromatic chemistry, reactions of aromatic compound that we'll probably cover in this chapter also. Some miscellaneous examples we'll see that we haven't done in phenol, right? So first we'll start with carbenes. Okay, we'll see the next intermediate. It is the next chapter, carbene. The reaction which involves carbene intermediate, okay, and then few reactions of aromatic compounds, again we'll see in this chapter. Okay, so write down the heading, carbene and aromatic compound. Carbene and aromatic compound. What is a carbene? Carbene is again an electron deficient intermediate. What are other intermediates we have, like the other intermediates which are electron deficient? Any example? Any example of electron deficient intermediate? Carbocation is an electron deficient intermediate. Carbanion is an electron deficient intermediate, right? Similarly, Carbene is also an electron deficient intermediate, right? The first thing you write down here, it is an electron deficient intermediate. Electron deficient carbon containing intermediate. Yes, carbanion is electron rich. You see this carbon, it has 5 electron, 1, 2, 3 plus 2, 5 electron. It's electron rich. Okay. So electron deficient carbon containing intermediate. Carbene, we have two types of carbene. The first one is singlet carbene. Singlet carbene. Singlet carbene is, in this what happens, we have carbon. Carbon has two sigma bond, like two atoms attached, atoms or groups attached with a sigma bond, X and Y. We have one lone pair and one vacant orbital on this carbon. This is carbene intermediate, singlet carbene it is. Why it is singlet carbene? Because if you count the spin multiplicity, if you calculate the spin multiplicity for this, spin multiplicity is 1 for this. That's why it is singlet carbene. Spin multiplicity is, they don't ask you to find out all this, but just I'll write down here, 2 summation of sigma s summation of s plus 1. So one electron here, it is there in the orbital, right? It is paired electron. So one is clockwise, other one is anti-clockwise. So value is 2, 1 into plus half plus 1 into minus half plus 1. So if you solve this, you'll get 1. That is the spin multiplicity we have. So carbene is singlet since its spin multiplicity is 1. Okay. Thus this value you can keep in mind, nothing much here. What are the properties of singlet carbene we have? Okay. The properties of singlet carbene, the first thing that you can observe here is it has 2 sigma bond and 1 lone pair, right? So it has 2 sigma bond and 1 lone pair. This properties based question also they ask sometimes, theoretical question. Okay, they'll give you 4 different statements A, B, C, D. Which one is correct for carbene, like that. Okay, that's why this property is important. So basically, if you know that structure, you can easily write down all these properties. So 2 sigma bond, 1 lone pair, and 1 vacant orbital. And 1 vacant orbital. So if it has 1 vacant orbital, it can accept electron pair. So it behaves as Lewis acid or electrophile also. Electron deficient, so electrophile. Okay. There's no charge on this. It is neutral because you see the carbon has 4 electron exactly. 1, 2, 3, 4. There's no extra electron. In the bonding state, if you see, it has 1, 2, 3, 4, 5, 6. Neutral, total 6 electron in outer shell. And hence 6 electron we have, it is electron deficient. And because of its electron deficiency, we have this 2 property, Lewis acid and electrophile, that we already discussed. Correct? This this carbene has 6 electron and hence it has incomplete octet. incomplete octet. Okay, it has bent shape sp2 hybridized. Okay, diamagnetic because electrons are paired. Diamagnetic. See, one orbital is vacant and the electron is paired. Ideally, what happens? Since it has a vacant orbital, this carbon atom should be here, according to Hund's rule, right? But this is not the case here. That's why this carbene, singlet carbene, does not follow Hund's rule. Does not follow Hund's rule. All these are properties of singlet carbene. Copy this down. Done. Okay, the next one you see is the first type of carbene we have. The second type is triplet. And yes, there is no duplet carbene. Okay, it's triplet. So if you see this triplet carbene, it has carbon with two bond and two unpaired electron like this. Two unpaired electron. So this two unpaired electron is present in two different orbital. Means the one which is vacant here, you see this, the one which is vacant here and one orbital has fully occupied. So this one electron is present in this orbital. So both orbitals has one electron, right? So this one, the triplet, it follows Hund's rule, right? This is triplet. Why we call it as triplet? Because if you count the spin multiplicity here, the spin multiplicity for this would be 2 times summation of s plus 1. Both electrons has clockwise orientation. So 2 into 2 electrons has clockwise, so plus half plus 1. And when you solve this, you will get the value 3, and hence it is triplet. Okay, this is the reason we call it triplet carbene. Now look at the properties for this triplet carbene. The first one is what? It has 2 sigma bond, but 0 lone pair. There is no vacant orbital. There's no vacant orbital. There are 2 unpaired electron. Unpaired electron. Hence it is paramagnetic. Paramagnetic. It is linear also, right? 6 electrons in the outer shell. in the outer shell, right? Electron deficient. Does this behave as Lewis acid?
No, sir.
Yes. It won't behave as Lewis acid because it has both orbital occupied. Not fully, but yes, it is occupied. So it cannot accept the pair of electrons. Hence, it is not a Lewis acid. It won't behave as a Lewis acid, right? It is biradical because we have two unpaired electron. So two radical we have, so it is biradical, right? And it follow Hund's rule. Right, so if they want to, you know, if they want to, frame some questions, theoretical questions on singlet and triplet, so these property you can, keep in mind. It is all depend upon its structure here, right? So if you know this, right, you can easily find out which statement is right and which statement is wrong. Yes, we'll do that, Siddharth. Just a second. See, if you talk about the stability of the two, singlet and triplet, right, then triplet is more stable because it follows Hund's rule, right? Triplet is more stable always. So write down the stability. Triplet carbene is more stable than singlet. But in the reaction, it is singlet that forms always. Okay, triplet is more stable than singlet, and we have what I said, singlet or triplet. Singlet forms always first. Okay, if I said triplet, this is corrected. Always singlet forms first. So there are some conditions for the stability of singlet carbene. If that condition is there in the reaction, it will remain as singlet only and take part in the reaction. If that stability is not there for the singlet carbene, then it will convert into triplet and take part in the reaction. Okay. Okay, so triplet is more stable than singlet, and in the reaction, it is singlet that always forms first, right? And the reaction proceeds. So first of all, what is the condition for the formation of a carbene intermediate? That you should know, right? Under what condition carbene intermediate forms, and what are the reactions we have in which the carbene intermediate forms? Obviously, when we have that condition present in any reaction, then it will form the singlet or triplet carbene, correct? So the formation of carbene, next heading you write down, under what condition carbene forms? Okay, there are four different conditions or reactions we have in which the formation of carbene takes place. All four reactions we'll discuss here. First reaction you write down, which forms carbene, is the reaction of chloroform CHCl3. We can also take the derivative of chloroform. The reaction of chloroform with any base, for example, we take KOH. You can also take NaOH for this purpose. Any strong base, then it converts into CCl2 with one lone pair and vacant orbital, plus we'll get KCl plus will get H2. This is the overall reaction we have. This compound, if you look at the name of this compound, the name is, it is dichlorocarbene. Okay, dichlorocarbene. Okay, it is not at all difficult, but a bit confusing. Okay, we have carbon and two random, atom I have written over here with one vacant orbital and lone pair. Correct. This X and Y could be anything. Here it is chlorine. It can be hydrogen and chlorine also. Anything is possible, right? So let's take care of that. Okay. So this is the one thing in which the carbon, carbene, intermediate forms. How this reaction proceeds basically. So the first step of this reaction, you see, the first step is the base, that is OH minus. This takes H plus from this chloroform, Cl, Cl, and Cl, which is easily understandable because both all these chlorine atom shows minus I, and this hydrogen becomes acidic in nature. So this one is acid-base reaction, forms H2O, and it forms a lone pair C with 3 chlorine atom present on this carbon and a negative charge on it. No doubt. Okay. Then with this, what happens? This trichloro product that we have, from this chlorine goes out as a leaving group because carbon has one negative charge, right? So, and chlorine is a good leaving group. So it goes out as a leaving group, takes this electron pair and goes out, and it forms carbon with 2 chlorine, right? One lone pair already we have on this carbon atom, and 2 electron is taken up by this chlorine. So this negative charge won't be there. And the electron which is taken up by this chlorine, because of that only, we have a vacant orbital on this carbon plus Cl minus. Correct? This Cl minus further combines with K plus, right, and forms KCl. Any doubt in this? All of you, please type in CLR if you understood this.
Sir, this is the final product, sir. It doesn't go under.
No, not at all. Not at all.
Okay.
Intermediate cannot be the, the final product of any reaction. These are not complete reaction, guys. All of you. These are not complete reaction. The reaction I have written. I will do all these 4 conditions under which the carbene intermediate forms. Okay. Then we'll see the reaction in which carbene intermediate forms and what the product we get here. So it is just a part of the reaction. Any intermediate, whether it's a carbocation, carbanion, free radical, carbene, nitrene, benzene, any intermediate can never be the final product of any reaction. So these reactions that I'm doing now, these are not the end product, right? These are not the end product of the reaction. Okay, so keep that in mind. This is just, these reactions is a part of, could be a part of another reaction. Okay, so this is the carbene intermediate forms, 1 vacant orbital, 1 lone pair, 2 sigma bond, and this is the intermediate, right? Write down few points here. See, one thing, let me just discuss here. This singlet carbene is not that stable, but depending upon the reaction condition, it may get stability. Just a second. Okay. Depending upon the reaction condition, it may get the stability. What are those conditions? The condition is, first of all, you see, this chlorine has lone pair. I'll just write down here, you see. I'm talking about, you can ask me, sir, why singlet retains in the reaction? Why not it converts into triplet? So that is what I'm trying to explain, that if singlet retains in the reaction, there must be some condition for that. You can have a singlet carbene with 2 hydrogen, possible, right? Like this, it is possible. Here it is carbon with 2 chlorine, right? But what happens here, this singlet carbene is not stable. We'll see what happens in this later on. This singlet carbene is not stable, but this one is stable because chlorine has lone pair on it, and this will stabilize the carbon atom by the back bonding. It donates its electron into the vacant orbital of this carbon, and that is how the singlet carbene becomes here stable. This is one thing. Did you get it, all of you? Right, so one thing is what, if back bonding is possible, like in this case it is happening, back bonding is possible, and the singlet carbene may get stability, right? It will get stability into this case. But in this case, since hydrogen does not involve in back bonding, it is not possible. So this singlet is not stable at all. This has to convert into triplet. How it happens, it's just the transfer of one electron into the vacant orbital. We'll discuss that later. But this is the one condition where back bonding is there and the singlet carbene forms, correct? Another condition is what, if the solvent is polar, then the polar solvent, suppose we have H2O, right? It donates its lone pair into the vacant orbital of it, and hence stabilizes the singlet carbene again. So two conditions we have under which the singlet carbene is stable. One is the back bonding if it is possible, and another one is the solvent if it is polar, which can donate lone pair into the vacant orbital of this carbene, and it stabilizes the carbene intermediate. All of you understood this? Tell me. Yes. Type in fast, guys, quickly. Okay. Fine. I hope you understood this. So this point you write down, this whatever I discussed just now, note write down here. All of you, singlet carbene forms where, wait Anjali, just you write it down, I'll repeat, wait. Singlet carbene forms where the stability is gained either due to resonance or due to polar solvent. Right, or due to polar solvent. Means we have two possibilities. One is back bonding should be there. If back bonding is not there, then the solvent should be polar, like H2O. Means right on the bracket after polar solvent, that lone pair should present, because this carbene intermediate, you see, I'm taking here suppose X and Y, right, and a vacant orbital. If you have lone pair present in the solvent, like suppose water, then this lone pair, it can donate into the vacant orbital of this carbene and stabilizes the carbene. So back bonding or polar solvent which has lone pair present on it, like in water. That is what the second condition we have, Anjali. Clear? For this reaction, we can take the base as OH minus. We can also take NH2 minus base. We can also take RO minus, PHO minus. You can have anything, right? So don't just memorize OH minus here. Any base and this kind of compound, chloroform. It's not like we always have chloroform in the reaction. I'll give you one reaction and you tell me what is the carbene we get here. Again, I'm repeating, these are not complete reactions. Okay, suppose we have a compound, say CHCl2 Br OH minus. What is the carbene we get here? Yes. Yes, we'll get here dichlorocarbon, correct? So how does it happen? First of all, this OH minus will take H plus, right? And we get here carbon with one lone pair and two chlorine atom and one Br here plus H2O. Now you have to understand one thing here, that in the mechanism, you see the last mechanism, one of the chlorine atom goes out, right? So we don't have any confusion here that which one will go out, because all are chlorine. If you have different atom here, suppose bromine, chlorine, iodine, like that, then the bond which is the weakest one, that one breaks easily, correct? So we have to remove the atom which has the longest bond length here. So fluorine, chlorine, bromine, obviously bromine has the longer bond length in comparison to chlorine. Then this goes out as the leaving group combines with whatever cation we have here, that is K plus if here, then KBr, and it converts into carbon with two chlorine and one lone pair and a vacant orbital plus Br minus. Okay, so this is the mechanism we have of this formation of dichlorocarbon. I want you to write down the carbene structure directly into this particular compound, CHCl Bri. One single step, write it down. The direct structure of this. Yes, iodine has a longer bond length. You have Cl Br, so I minus goes out, and the carbene would be Cl C Br, lone pair, vacant orbital, I minus, and H2O. Clear? No doubt. This kind of compound you may get in the reaction. Okay. So this happens when we have chloroform, CHCl2. This is the one condition under which carbene forms. A very similar, reaction we have here, that is tetrachloromethane, which is nothing but, write down the second reaction in which the carbene forms. First reaction we have done, we have tetrachloromethane, CCl, Cl, Cl, and Cl here. Right, I want you to compare with the first reaction, that is chloroform wala reaction, right? What happens into that? Instead of one chlorine, we had hydrogen, and we were taking a base over here, so that base OH minus takes this hydrogen, forms H2O, and then one of the chlorine goes out, right? That is what happening in the previous reaction. So if we are able to remove any one of the chlorine atom as Cl plus, right, then the same thing happens, yes or no? Agreed? Tell me. If we are able to remove one Cl plus, like we had removed H plus over there with OH minus, then the same reaction would be there, right? So we'll take the reagent here so that we are able to remove the Cl plus from this particular molecule, right? And the reagent would be a strong base we take, and that is R minus and Li plus. This R minus takes this Cl and forms RCl, Cl plus forms RCl, right? And this carbon again converts into 3 chlorine atom here with 1 vacant orbital. And you know what you have to do after this, right? And that when this Cl minus goes out, it converts into dichlorocarbene, correct? And the Cl minus that goes out, it takes this Li plus, forms Li. Any doubt in this? Do you want me to write on the mechanism here? It's simple. R minus takes this chlorine. This bond pair is here, forms R scale and this, and then we'll have this reaction. Okay, this comes out. Clear? Leaving group ability we know for halogens. I we have maximum, then we have Br, then we have Cl, and then we have F. Okay. Write down one note. In these reactions, in this reaction, we always get singlet carbene first. In these reactions, we always get singlet carbene first. And if it is not stable, singlet carbene, if it is not stable, it converts into triplet. If it is not stable, it converts into triplet.
Sir, can you repeat?
And when the carbene won't be stable, if the medium is non-polar or gaseous phase reaction, and when there is a absence of back bonding, write down these points. If the medium is non-polar or gaseous phase, if the medium is non-polar or gaseous phase, then the carbene is not stable. Sorry, gaseous phase or in absence of back bonding. That also you write down. Non-polar or gaseous phase or absence of back bonding. Singlet carbene is not stable and converts into triplet. Again, I am repeating this. In absence of, if the medium is non-polar, gaseous phase, or in absence of back bonding, non-polar gaseous phase, or in absence of back bonding, the singlet carbene is not stable and it converts into triplet. What is the carbene we get in this reaction? Could you tell me? We have CH3 Br with CH3 minus Li plus. That's not correct. I need to. See one thing here. You cannot break this carbon-carbon bond. Okay. You cannot break this bond. That's correct, Siddhartha. You cannot break this bond. So this CS3 must be present in the carbene. Means one atom here, it is CS3. Right? So what happens like this, you see R minus take this one of the chlorine atom. This R minus, that is CS3 minus, will take one of the hydrogen atom here. Okay. So which atom is easier to extract? Which hydrogen atom? The atom whose bond length is more, that is Br. So what happens here? Yes. So what happens here? This CH3 minus takes this Br, right? This bond pair comes over here and it forms CH3Br, right? And then what happens? One of the chlorine atom goes out as leaving group. Li plus will take that chlorine atom, so Li is Cl, and the carbene that we get is CS3 as it is carbon, chlorine, one lone pair, and vacant orbital. Clear, all of you? One more point you write down. These reactions are not complete reactions. Just a second, Aditya. These reactions are not complete reactions, and this could be a part of any other reaction. Okay. Okay. If, see Aditya, across carbon, any group if it is present, then it can show this kind of reaction. The only thing is what? You must have one leaving group, one good leaving group, right? And one atom like this present, which can be taken up by the base like this CS3 minus, or one hydrogen is there. Like suppose, if you're talking about this pH, right, Cl, then H and CS3.
Yes, sir.
We have a base, suppose OH minus. OH minus takes this H plus and it forms carbon, pH, Cl, and CS3. And then this Cl goes out. It takes this bond pair and goes out. It's possible here. But if you have CS3 present here, then with OH minus it is not possible. Even with CS3 minus also it is not possible, because this will take this Cl, but after this, this bond won't break. Carbon, 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 carbon bond. So it depends that along with pH, phenyl group, what are the other groups or atoms attached to it.
Okay, sir. Thank you.
Clear?
Yes, sir.
Aditya, what happened? Sleeping? Aditya C, yeah.
Yes, sir.
Okay, these are the two reactions under which um, carbene intermediate forms. The third one is, write down, the third one with diazomethane. All these conditions and reactions you have to keep in mind, because then they won't ask you and tell you that this in this reaction the carbene intermediate is forming, right? So you should know this under what condition carbene intermediate forms. Diazomethane is, we have CH2 double bond N, double bond N, positive charge, 2 lone pair on nitrogen, negative charge. When you heat this diazomethane, or if you write high temperature, or in presence of light, any one of the three conditions, right? It converts into a carbene, which is this, and nitrogen gas evolve into this, right? But this carbene, you see, it is not a stable carbon, because there's no back bonding and medium is also not polar here, right? So this is not stable, and it converts into triplet, which is this. So triplet you can write like this, 2 clockwise electron, or you can also write this way. Carbon has 1 electron this and 1 electron in the vacant orbit. This way also you can write. Okay, I'll write down how the reaction proceeds. This one here. We have CH2 double bond N, double bond N, 2 lone pair, negative charge, and 1 positive charge. If you write down the resonating structure of this comes over here, this comes onto this carbon, and hence we get a lone pair on this carbon atom, which is this sigma bond N, triple bond N, positive charge, negative charge. Then after this, what happens? Since we are heating it, it takes this bond pair of electron, goes out as N2, and we get a vacant orbital on the carbon atom. So we get this simple one, and a vacant orbital on the carbon atom. Okay, and then it converts into the triplet. Fourth condition in which carbene intermediate forms is exactly similar to diazomethane. Okay, the name of the compound is ketenes. So ketenes is this one, CH2 double bond C double bond O. If you compare this two, it is exactly similar. Instead of this nitrogen, we have carbon, and this nitrogen, we have oxygen. Here, this nitrogen has 2 lone pair. Oxygen also has 2 lone pair. Okay. And the condition also, it is same here. We can heat this or at high temperature or in presence of light, any one of these three. It converts into same thing, singlet first and then triplet. Exactly same we have over here. Okay, you can easily understand this here. This comes over here. This goes here. And then this sigma electron is taken up. The sigma bond breaks and the electron base taken up by this carbon forms CO and we get. No doubt regarding the mechanism of this reaction. Exactly similar to the previous one. So these are the four reactions in which, or conditions in which, carbene intermediate forms. Okay. Like I said, these reactions are not complete reactions. This could be a part of any other reaction. So now the next thing we are going to understand what all reactions we have in which carbene intermediate forms and what is the final product we get in those reactions. Okay. So write down the heading. Reactions of carbene. Reactions of carbene. There are total 8 reactions we have which involves the formation of carbene, and those reactions are, the first one you write down, addition on alkene, addition on alkene. The second one is carbyl amine reaction. Amine reaction, very important one. This is the reaction of 1 degree amine, primary amine. We use as the test of amines. Okay, we'll discuss this also. Third one is Reimer-Tiemann reaction. Had discussed in the last class, that we'll discuss it here. I told you already. So it is Reimer-Tiemann reaction. Reimer-Tiemann reaction. The fourth one is Arndt-Eastert reaction. Reaction of carboxylic acid. The fifth one is reactions on carbonyl compound. All these reactions you see we are discussing here, carbonyl compounds, many reactions we have seen in the oxidation reduction reactions. Few will see here also. The next one is insertion on alkanes. Seventh one is acid-base reaction. Acid-base reaction. And eighth one is Simon-Smith reaction. Simon-Smith reaction. These are the 8 reactions which follows which form in which carbene intermediate forms. First reaction you write down. Addition on alkene. Write down this reaction involves both mechanisms, singlet and triplet. Okay. It involves both mechanism with singlet carbene and with triplet carbene. Singlet and triplet. Okay. Singlet one is very simple. Okay. Just for the both one, you should know the one properties. There's only one difference in the two reaction. Okay. The triplet mechanism is factual. Okay. You should understand that this is how it happens. Okay. I'll tell you what you have to keep in mind. But suppose I am taking, I'll write down one property here. The singlet one is stereo specific. The singlet mechanism that you have is stereo specific, and the triplet one we have is non-stereo specific. That is the difference we have in the two mechanism, and on this difference only they ask question in the exam. Obviously you should know that what is the product we are getting, but the property you should understand the difference between. Stereo specific means what? When you have cis alkene, if you're taking, then the product would be a cis product only. You won't get trans here. If you are taking trans alkene, then it gives trans product. That is what it means, stereo specific. Either you get cis or trans. You won't get both. Non-stereo specific means what? You are taking cis alkene, but you are getting cis as well as trans. Okay, so you don't have any control on the stereo aspect of the compound, right? So cis gives you cis and trans both. Got it? That is what the meaning of stereo specific and non-stereo specific we have. Okay, I'll write down the reaction. First you copy this down. I'll go to the next page. Done? Okay. So first of all, we'll see singlet carbene mechanism. Suppose we have a cis alkene, we are taking C double bond C, CS3H and CS3H, and this is allowed to react with, suppose we have CHCl3 here in presence of a base KOH. Like this, you see this kind of reaction you will get. They won't write down here carbene or something else. They won't write down directly CCl2 carbene. So you should know that this reaction gives you carbene intermediate, the first type that we have discussed, right? The product that we get here is carbon-carbon. This CS3 would be as it is on the same side, like it was present initially, right? And one pi bond breaks, and this carbon will be attached with the carbene that is chlorine and chlorine. This is what the product we get, right? So it is stereo specific.
But isn't this unstable?
Stereo specific. Cis gives cis, trans gives trans. How it happens, again, I won't write here the formation of carbene and that mechanism. I'll just give you that this particular thing reacts and it gives carbene intermediate, right? This gives carbene intermediate. We have already seen how it forms carbene intermediate. And this carbene intermediates reacts with this. See this one? Carbon has 2 chlorine, right? 1 lone pair and vacant orbital. So what happens? This attacks onto this carbon. This pi electron shift over here, right? We'll get a negative charge, pi electron shift over here. And this negative charge, it again attacks onto the vacant orbital of this carbene. Right, so this carbon pi bond breaks and this joins with this, gives you this particular compound. Tell me, understood this? We are not consider here, Anjali, the stability of the compound. Obviously, 3-membered ring is not stable. But if they ask you the product forms in this one, this is the possible product only. We are here, we are discussing with the reaction, right? So what product may form? That is a different debate, that whether the product is stable or unstable. Okay. Yes, that's what Tripan I was about to say. This carbene, we have 1 lone pair and vacant orbital. See, look at the property of this. Very unique property it has actually. It has 1 nucleophilic end, right? 1 lone pair, so it has 1 nucleophilic end. And since vacant orbital we have, so it can accept electron also. So this is the electrophilic end we have. So it has both end. It loses electron also and gains electron also, electrophilic end. Clear? Got it, Tripan? Fine. The next mechanism you write down, a triplet mechanism here. We know it is non-stereo specific. I've already written this. And non-stereo specific means non-stereo specific means cis can give cis as well as trans. Okay. Suppose we have this reaction. We have C double bond C, and we are taking a cis alkene here. CH3H cis alkene, and we are taking diazomethane, gaseous phase. CH2 and 2 gaseous phase we have, or we can write down in presence of H nu. Both we can write. Okay. The product that we get here is, one is the cis product, which is this one. And the carbon we get here is CH2. Right. So one hydrogen is this side and one CH3 is this side. One hydrogen is this side, one CH3 is this side. Along with this, we also get the other product where the hydrogen is this side, CH3 is this side, CH3 is here, hydrogen is here, and here we have carbon with H. This is what non-stereospecific means. It gives you cis as well as trans. See, how does this reaction takes place? We have alkene, which is C double bond C, CH3, CH3, H, H, and the triplet carbene, right? Triplet carbene is this. Carbon has 2 hydrogen and two clockwise electron, right? This pi bond, you see, this pi bond here, one electron is clockwise, other one is anti-clockwise. So if I draw this pi bond, like if I remove this pi bond here, and the electron that is present in this pi bond, if I write down this electron as one is clockwise and other one is anti-clockwise. Okay, so this clockwise and anti-clockwise electron, this one and this one, can easily make a bond, right? So that is how one bond forms over here. Carbon, carbon, single bond. This is the carbon with one bond. Sorry. Carbon with one bond, right? One we have clockwise orientation. This one has clockwise orientation. H, H, and all other things is as it is. Correct. Now this one is trying to interact with this. To make a bond here, there must be spin inversion. Spin inversion means what? The orientation of electron must change. Clockwise must becomes anti-clockwise, one of the electron, right? This is one thing. Spin inversion takes. Obviously, this will interact with this. Then one electron invert and forms a bond. That is what it happens. But during this spin inversion, what happens? Already you see the pi bond has been dissociated here, has been broken. There's no pi bond present here. And across single bond, the bond rotation is possible. So there are two things. One is spin inversion and one is bond rotation. So it is a fact, and we observe that the time required for this spin inversion to make a bond here is more than the time required for this bond rotation. Right? So bonding of both electrons, like the bond rotation requires lesser time, right? Hence, by the time this spin inversion takes place, this sigma bond rotates and it gives the other product, that is the trans product we have. So one possibility is what? If at point, suppose if this invert and this make a bond, then we'll get cis. And when the bond inversion takes place, then it converts into trans. And that is how the product forms here. So I'll write down here only, again I won't write. This bond becomes anti-clockwise, and it gives you this. So obviously we cannot, I cannot show you this. It happens sometimes. This bond forms very fast, right? And sometimes it bond rotates also, so it gives you cis as well as trans. That is how the product forms. Okay, and that's how I said that this one is a bit factual. Okay, so you have to memorize this. So sometimes they ask this thing, that is, uh, the theoretical question on this. Just one change, just a second, guys. Just one change here. One, you write down this way only, and then we can write down this way. It would be better that we get both trans as well as cis. Better way to represent this, correct? So reason is what? The time required for spin inversion is more than to that of bond rotation. Why bond rotation is feasible here? Because the pi bond dissociates. Sigma bond we have, and rotation across sigma bond is not hindered. Write down, the time required for a spin inversion is more than that of bond rotation. Hello.
Yes,
Can you
sir.
hear me?
Yes, sir.
Yeah, hello.
Yes, sir.
Guys, my laptop turned off. It was not connected to the um, power. I won't be able to send you the notes. The entire thing is gone. All of you have copied, no?
Yes, sir.
Yes.
Yes, sir.
Yes. So today I won't be able to send you the notes. I'm sorry. Okay. So the last reaction you have done, no? You have written all of you, last reaction, cis and trans. Okay. So two different mechanisms. If it is singlet carbene, gives you stereo-specific product. Cis gives cis. Yeah. The last point was the time taken for a spin inversion is more than the time required or time taken. The time required for a spin inversion is more than to that of the bond rotation, and hence we get both product, singlet as well as cis as well as trans. Okay. Mechanism here, it is not important. You should know when you are getting this thing, singlet carbene, and when you are getting triplet carbene. According to that, you can write down the product, whether it is cis or trans product. Correct. Now you look at this question here based on the reaction we discussed just now. Yeah, you look at this question here. The question is, this is the alkene. This is allowed to react with CHCl3 with KOH, and in the next reaction it is allowed to react with CH2CO, and we are heating it. Product you write down in this reaction. What is the product we get in this reaction? CH2N2 gaseous phase, and we are heating it. We have CHCl3 KOH, CH2CO excess we are using, try all this. Done, all of you? See, the first one, the carbene that we get here is singlet. First of all, you should identify this. It is singlet carbene. This one is what? This one is triplet. This one is again triplet. This one is singlet. And this one is triplet. So we know triplet carbene gives cis and trans both, if possible, and singlet gives you only cis, stereo specific, right? So since it is singlet, so this would be stereo specific, and the product for the reaction is this would be as it is, right? And here we get CCl2 attached here. Correct? No doubt. We have hydrogen. Here we have hydrogen, CS3, C2H5. In this case, we are getting triplet. Okay, we are getting triplet. So one of the product is this, plus the another product is this. Yes or no? Just you need to focus across the double bond what is happening. That is it. You see, at double bond only the triplet, the carbene get attached. No, so you'll get a 3-membered ring obviously here. That is what we are getting. In this also here we get a 3-membered ring, right? And the product would be a 6-membered ring like this and a 3-membered ring like this. I have drawn this in a different way, but it is the same thing. And since there is no GI here, there is no point of cis and trans isomer here. Only one product we get. In this also, it is singlet, so we'll get what? This Cl and Cl. This is in excess. So here we don't consider resonance and all, right? That is not here we are discussing. Here it is possible. The reaction takes place at the double bond. CS2, so we'll get a ring here like this, and we'll get a ring here. Again, you see, geometrical isomerism is not possible in the last one. So we won't talk about cis and trans. Tell me, any doubt in this? Okay, can I go to the next page?
Yes, sir. Yes, sir. We can change page.
Write down the product in these two reactions. The first one is CHClBr2 with KOH, and the another question is plus CBr4 reacts with RLi, gives A, again reacts with RLi, gives B, reacts with this alkene, gives C. What is A, B, and C? What is the carbene in the first reaction? What is the carbene we get in the first reaction?
CClBr.
CCl and Br. Okay. CCl and Br gives you both cis and trans here. Sorry, it is singlet. So what is the product we get here? Cl Br. Yes.
Yes, sir.
Okay. Now in this one, you see the first step. First we get the carbene, which is CBr, Br, right? And it is a stable back bonding is there, and we get this, correct? This reacts with this, and A that we get here is we have a 6-member ring and a 3-member ring here with Br and Br. Clear? Okay, now when this reacts with RLi, again you see this reaction is the reaction of formation of carbene only. 2Br, again it forms RBr, LiBr, and you get here another carbene, which is this. This is the carbene that we get, and it is B. The carbon has 2 sigma bond and 2 carbene here, 2 unpaired electron, right? Triplet it forms because there is no any stabilizing agent we have here, right? Now this reacts with the alkene, which is this, to give C. So what we get here, this carbon attached with this carbon, and the product C here is this one. We'll have a 6-membered ring. This attached with this carbon and 2 methyl group here. One is cis, since this one is triplet, we also get trans here, and that one is this. Did you get it? Understood?
Yes, sir.
Fine. So this is it for this addition of alkene. The next reaction we'll do Reimer-Tiemann reaction after the break. Okay. So we'll resume the session at 7. Take a break now. Hello guys. Shall we start? Okay. So addition on alkene, we have seen the reactions and many examples. The second reaction we have, which forms carbene intermediate. Write down the second one. It is Reimer-Tiemann reaction. Reimer-Tiemann reaction. Reimer-Tiemann reaction, it is a reaction of phenol. Okay. And in this reaction, phenol reacts with CHCl3 in presence of KOH and forms salicylaldehyde, which is this ortho and para product. Okay, so this one is ortho salicylaldehyde, this one is para salicylaldehyde. Okay, ortho one is major here because of hydrogen bonding. Right, the name of the compound is salicylaldehyde. Okay, if you have COH here, it is salicylic acid. Clearly you see the medium is basic first of all. So basic medium converts this into phenoxide ion O minus, and then you draw resonating structure, you'll get a negative charge over ortho and para position. Okay, so I'm just drawing this one directly where we have ortho and para position. Attach here we have the negative sign, right? And this reacts with the carbene intermediate, which is this, forms, right? And then this electron pair, it donates into this carbene intermediate. Okay, so this converts into double bond O, pi bond, and here we have one H present on this ring, Cl and Cl. Okay, one lone pair we already have on this carbon atom. From this H plus comes out to maintain the aromaticity of the ring. This H plus, it donates its electron pair here, pi electron shifts over here, and this H plus is taken up by this carbon and it forms double bond, double bond, double bond, O minus CHCl2. Okay, CHCl2. Chlorine here is a leaving group, and then OH minus attacks onto this, and one chlorine goes out from this. See this one? Chlorine is a leaving group. Mechanism for this one is not that important. Okay, let me tell you this. And this chlorine goes out as a leaving group, and it converts into O minus on the top CH, OH, and Cl. Okay. Now from this lone pair forms a pi bond. H plus comes out here, and this pi bond forms this Cl minus goes out, and this H plus is taken up by this O minus, and it converts into OH on the top, CHO here, and Cl minus goes out. This is orthosalicylaldehyde. Same mechanism is possible at para position also. You'll get para product. Understood? Okay. Done, all of you? Now in this only, Reimer-Tiemann reaction is this. There are some reactions which takes place according to this mechanism only, means similar mechanism we have as we had in the previous reaction, Reimer-Tiemann reaction, and we call it as miscellaneous Reimer-Tiemann reaction. Okay, miscellaneous Reimer-Tiemann reaction. So you see this reaction, it's a different, we'll get a very unexpected product in this reaction. You see, if you have a 5-membered ring with a double bond like this, and when it reacts with CSCl3 in presence of KOH, the product that we get here is benzene and one chlorine attached over here on the benzene. This is the product we get. Let us try and understand how do we get this product. So obviously, you see this hydrogen is, it can easily give this hydrogen because the ring becomes aromatic. Okay, so this OH minus takes this H from this, and it converts into, an aromatic ring, which is this one. Okay. Okay, and the carbene intermediate that forms because of these reagent, the carbene intermediates, it reacts with, we know the double bond has more nucleophilicity, so it reacts with this double bond and it forms the product similarly like we had in addition of alkene, and it gives you this product. Chlorine here, and this lone pair would be as it is, this double bond would be as it is. Is it clear, all of you? Please tell me. This reaction is the reaction on double bond. Yes, tell me, guys.
Yes, sir.
Yes, sir.
Okay. Now you see this. If you number this carbon atom, it is 1, it is 2, it is 3, 4, 5, and 6. what happens, this lone pair, it forms a pi bond here, and the bond between 2 and 6, right, it breaks and it comes over here onto this 6th carbon atom, right? So we'll get here a 6-membered ring in the next step. We'll get here a 6-membered ring where we have the negative charge on the 6th carbon. First carbon has 2 chlorine attached with it. So it is 1, it is 2, 3, 4, 5, and 6. We have a double bond between 2 and 3. So we have a double bond here. Double bond between 4 and 5. We have a double bond here. Then what happens in the last step? You can understand it easily. This lone pair forms a pi bond here. This lone pair forms a pi bond and 1 chlorine goes out as a leaving group from this. So this converts into a benzene ring and chlorine at 1 carbon. This is miscellaneous Reimer-Tiemann reaction. Clear? So the reagent of Reimer-Tiemann reaction is CHCl3 with base. KOH, NaOH, you can take any base. Write down the product in these reactions. Five-membered ring, CHCl, BRF, KOH. Similar one, it is CHCl, Br2, KOH. Write down the product. Tell me the product. Which halogen atom will attach with the 6-membered ring in the 2 reaction? Yes, the one in which the bond is the strongest one, that would be present at the ring, right? So obviously this 5-membered convert into a 6-membered ring, benzene ring, and fluorine will present over here. In the second case, it converts into a 6-membered ring and chlorine present on the ring. Okay? Yeah. Now the next reaction, the third one, write down. That is carbyl amine reaction. Carbyl amine reaction. This is the reaction of primary amine. This is the reaction of primary amine. Only primary amine gives this reaction. Secondary and tertiary, does not show this reaction. Okay, and this question they ask in exam many times. Okay, so must remember this. CSCl3 with KOH, it converts into RNC. Okay, isocyanide it forms. This isocyanide gives a foul smell, and that confirms the presence of primary amine in this. Okay, primary amine. So look at the mechanism here. The mechanism, by the way, it's not very important, but why this reaction is shown by only primary amine, that you would understand once you understand the mechanism. Okay, but mechanism based question is not possible here, right? So let us discuss this quickly. Obviously this gives what? This gives carbene intermediate, and this carbene intermediate reacts with amine, which has lone pair on this, and it donates the lone pair into the vacant orbital of this carbene. Okay, and this step is the RDS of the reaction, rate determining step. Converts into RN carbon, chlorine, hydrogen, positive charge on nitrogen, and a lone pair on carbon atom, right? It accepts the electron, so we have a negative charge. Now you see this, if the positive charge on nitrogen, it is not stable, this H plus, it rearrange itself onto this carbon atom. This we call it as proton exchange. You can understand this as proton exchange, or H plus comes out and which is taken up by this C minus. So it forms what? R N C H Cl Cl H and a lone pair. Right? Now since this we have two living group here, then what happens? This lone pair forms a pi bond here, and one leaving group goes out from this, and it converts into R N double bond CH Cl H and positive charge on this. Okay. Medium is basic, we have KOH. So this OH minus takes this H plus and makes this nitrogen stable. Again the same thing, this comes over here and Cl minus goes out from this as a leaving group, and it forms R N triple bond C, positive charge, and H here. Again what happens, last step is basic medium, OH minus takes this H plus, forms RN triple bond C, negative charge and positive charge, which if you take here, right here the coordinate bond, it would be like this. Both are the same thing, isocyanide, cyanide, fall smell. Finished? Tell me. Okay. First question, why secondary and tertiary amine does not show this reaction? Okay. So now you see, we are talking about secondary amines. Just you say this green color, right? If it is secondary amine, so instead of one hydrogen, we'll have one R group present, correct? So here also we have one R group present. This is possible, right? Here also we have one R group present. Here also we have one R group present, right? Till here, the reaction is possible for secondary amine. After this base cannot take this R, right? Because this is not a good, leaving group. It won't go out with this O minus, right? That's why after this step is not possible if you have secondary amine, correct? So finally, isocyanide won't form. If it is tertiary amine, then here itself that proton exchange is not possible. First step itself is not possible, right? This forms, but next step is not possible. So this positive charge is highly unstable here. Reaction goes in backward direction. That is why primary and secondary amine, secondary and tertiary amine does not show this reaction. Understood this? This is one thing. Since only primary amine shows this reaction, so this is a test of amines also. Write down, we can easily differentiate primary amine from secondary or tertiary amine by this reaction. We can easily differentiate primary amine from secondary or tertiary amine by this reaction. Okay. Second point is what? Is about this RDS, important one, right? This carbene, if it has more tendency to accept electron, more will be the rate of reaction, right? More tendency to accept electron and the rate of the reaction would be more. When carbene has more tendency to accept electron, if the carbene is less stable. If it is less stable, it wants to take electron from that nitrogen atom, and hence more will be the rate of the reaction. Okay, so write down unstable carbene. Next point, unstable carbene has more tendency to accept lone pair. Unstable carbene has more tendency to accept lone pair, and hence more will be the rate of reaction, right? So if you talk about the carbene forms with chloroform and bromoform, like in this one, CHCl3 and CHBr3. The carbene forms from this is CCl, Cl, lone pair and vacant electron. This one has CBr, Br, lone pair and vacant electron. Okay, now which carbene is more stable? Could you tell me? Which carbene is more stable in this two? If you can compare. CBr2 is more stable. No. You see, carbene would be stable if we have back bonding possible, right? If back bonding is possible, then the carbene would be stable. Here, if back bonding is taking place, carbon has 2p orbital and chlorine has 3p orbital. So it is 2p, 3p overlap. Here it is 2p, 4p overlap. So which overlap is better? 2p, 3p or 2p, 4p? 2p, 3p or 2p, 4p? Which overlap is better? right? Similar, yes,
2p3p.
similar size orbital has better overlap, right? As the size difference increases, overlapping tendency is less, right? So 2p 3p orbital has better overlap, hence stability order is this. Stability order. And this carbene is more stable, right? It means it has less tendency to accept electron from the nitrogen atom, right? So CHBr2 has more tendency to accept electron. Hence, the rate of the reaction, if you compare for this two carbene, in case of this two carbene, this is the rate of reaction we have. CHBr2 will give better rate towards this reaction. Any doubt here? No doubt. So this is with respect to the carbene that you are getting. Second point is what? If you have to compare the rate of the reaction, we can also compare the electron donating tendency of this nitrogen. More electron donating tendency, more will be the rate of reaction, right on this point. As the electron donating tendency of nitrogen increases, rate of reaction increases. As the electron donating tendency of nitrogen increases, rate of reaction increases. Okay, so compare the rate of reaction in all these compounds. The first question is aniline and this one. Rate of reaction in this two. Compare the rate of reaction. Done? Okay, the first one you see, nitrogen, the lone pair is in resonance, has less tendency to donate. So this one has the more rate of reaction. Second one, again, it is in resonance, right? This one has more rate of reaction. It has more electron releasing nature. First one has more electron releasing tendency, the rate of the reaction is this. Okay, so this kind of thing, basic concepts of GOC you can apply, and you can find out the electron donating tendency of nitrogen and compare the rate of the reaction. Okay. Next reaction you see, the fourth one, and this reaction is Arndt Estert reaction. Okay, this reaction is for carboxylic acid. Okay, reaction is RC double bond O OH, and when it is allowed to react with the first one, first reagent is SOCl2, the second reagent is diisomethane CH2N2, then the third reagent we are using is Ag2O, we are heating with Ag2O. Fourth reagent we are using basic solution, aqueous basic solution, right? OH minus H2O. We can also take here in the fourth step, can also take RO minus with alcohol, right? The solvent must be the conjugate acid of this base. OH minus is the base, its conjugate acid is H2O, that is a solvent. RO minus is the base, conjugate acid is ROH. So when you take these four reagent, the product we get here is R and C double bond OOH. In between the two, you need to insert one CH2, and the product is this. That is it. This is the product we get. You should know how to write down the product because mechanism we'll see, but it has a complex mechanism. Okay, but the product you should memorize how to write down the product plus reagent. See, first step of this reaction is we have acid RCOH. This reacts with SOCl2, and this reaction, if you remember, we have done this. SOCl2 convert this into acyl chloride. Right. Sulfur dioxide evolves. HCl also forms in the gaseous phase. It also escapes into the atmosphere. Second step, this acyl chloride this reacts with CH2 and triple bond N, positive, negative, diisomethane. Okay, this attacks onto this carbon atom and this goes out as a leaving group. Product is R C double bond O CH2 and triple bond N, positive charge on it. Okay. In the third step, this Ag2O silver oxides oxide behaves as a base, and it takes this hydrogen, which is slightly acidic because of this C double bond O and triple bond N positive charge, plus Ag2O. Oxygen has lone pair, so it takes this hydrogen, leaving this bond pair of electron behind, so it forms R C double bond O CH lone pair, single bond N triple bond N positive charge on it. Plus we get here what? Ag2OH positive charge. From this Ag2OH, Ag comes out and that combines with this Cl minus which comes out here and forms AgCl as the another compound. After this, what happens, you see, this N2 goes out as easily. It takes this electron pair and goes out. And when this goes out, you see, we get a a vacant orbital here on this carbon atom. Lone pair is already there. A vacant orbital we get here. Just a second. Right, vacant orbital is already, electron pair is already there, plus a vacant orbital because the electron pair is taken up by nitrogen. This is now here you have to take care of one thing that you haven't done before. This is the carbene intermediate, right? See, this is the carbene intermediate. One rule you write down here: whenever carbene intermediate forms adjacent to the carbonyl carbon, means C double bond O group if it is there, whenever carbonyl carbon, carbene intermediate forms adjacent to the carbonyl group, then Wolff rearrangement takes place. Wolff rearrangement takes place. WOLF, WOLF, Wolff rearrangement takes place. Right? Wolff rearrangement takes place. What is Wolff rearrangement? It is the arrangement of this alkyl group. It takes the electron pair and rearrange itself onto this vacant orbital of this carbon atom. And this lone pair jumps over here, forms a pi bond. So this we call it as Wolff rearrangement. WOLF, Wolff rearrangement. Okay, this you must remember. It takes place whenever the carbene intermediate forms adjacent to the carbonyl group, that is C double bond O. So it converts into R CH double bond C double bond O, and we have what? Nothing. This forms, right? Now after this OH minus, we have base. This base attacks onto this carbon, pi electrons shift over here. It forms R CH lone pair negative single bond C double bond O OH. Correct? Then this minus get protonates from H2O, or we can say like this: there's a proton exchange with H2O, it gets protonate and it converts into RCH2 C double bond O. This is the mechanism of this. Like I said, all these mechanism you are not going to draw this, write this in the exam. So you have to basically, you should know the reagent that we are using, because the reaction you will identify from the reagent itself. So you have to memorize the reagent, what reagent we are using in its step, and then you can write down the product. Clear? Then can I move on to the next page?
Yes, sir.
This wolf rearrangement is very common in nitrines also. Same thing happens with nitrines intermediate also. We'll discuss it there also. Okay. Next reaction, the fifth one, write down. Acid-base reaction. This reaction is possible with the molecule which has active hydrogen. Active hydrogen, I have told you already, hydrogen attached with oxygen, fluorine, chlorine, bromine, sulfur, all those, right? So, suppose we have an alcohol, ROH, reacts with diazomethane or ketenes, CH2CO, and we heat this. Nothing you have to do, O, just you have to insert CH2 between oxygen and hydrogen, that is it. Okay, very simple mechanism you see. We have ROH, alcohol. This reacts with the carbene intermediate. It donates lone pair here, converts into ROCH2, negative charge, H with positive charge. Then to stabilize this positive charge, H plus comes out, and this H plus rearrange itself onto the carbon atom, that we call it as proton exchange, forms this product. Okay, very simple one, very simple reaction. This one is, write down the product in this reaction. CH3CH2, C double bond OOH with CH2 and 2. OH with CH2CO, carbon 14, and we are heating it. Product is the CH2 will get inserted over between this oxygen and hydrogen. Product is CH2, CH2, CH3, CH2, C double bond O, O CH2H. Here also we have the phenyl ring, OCH2H. Okay, this carbon is carbon 40. Okay. Can we think of triplet carbene here?
It won't be possible.
Can we think of triplet carbene here? Is it possible to get triplet carbene? Is this singlet carbene stable?
No, sir.
It will be stable. There's acidic hydrogen.
Why triplet carbene is not forming here?
So there's acidic hydrogen.
Anyone? Acidic hydrogen we have, right? So the alcohol is a polar medium, right? Acidic hydrogen. No, it is not. Were you talking, Tripan? I was not getting.
Yes.
It's fine now. Anyways,
Okay, sir.
so since we have acidic hydrogen here, right, you see we have oxygen lone pair. So this will stabilize the carbene here. Hence, it won't convert into triplet. Okay, we'll consider singlet and we'll get the product. Now, next reaction we write down. The sixth one. Reactions on carbonyl compound. Reactions on carbonyl compound. So carbonyl compound suppose we have this one double bond O reacts with CH2N2 and we heat this, it converts into two products it gives. One is this, and other one is, it's a single bond, and other one is this one. And double bond O. This reaction, you see, this product is very similar to the previous one we have, where the Arndt ester reaction, where the CH2 group insert between the alkyl and carboxylic acid group, right? Same thing we have here. This product is KCP, fast forming product. This is TCP, stable product, slow forming, stable product, right? Three-member ring is not stable, right? And that is the fast forming product we have. Okay. Now you see here how the reaction proceeds. Diisomethane, the carbon which has a lone pair on it, plus CH2 and triple bond N, positive charge, negative charge. Okay. So what happens? This attacks onto this carbon. This goes up, pi electron onto that oxygen, converts into and this we have O minus. Okay. When we heat this, N2 goes out and it converts into carbene intermediate. We have O minus. Here we get CH2, one vacant orbital, and lone pair is already there. Then this oxygen donates its lone pair here into this. Oh, I missed this. This one we have two now. One more we have here, and one more here, right? So what happens? This carbon, something I've done something. That's what I did. This should not be here. It is on the carbonyl carbon. So this is present over here. That's why I was getting 4-membered ring, right? Then this comes over here, and this converts into this one. Oxygen with CH2, and this bond we already have, right? So this is one possibility. Fast forming product, it is KCP. Another possibility is what? That here, this donates its lone pair. The another possibility, I'll write down here what happens. We have this O minus, and here we have CH2, lone pair vacant orbital carbene. Another possibility is that this donates its electron pair, forms a pi bond here. This electron pair shift here, and this attacks onto this vacant orbital of this carbon, and it converts into, see this double bond O, the CH2 of diisomethane is here, and this group get attached with this carbon, so it's like this. And hence the product is this. KCP forms at high temperature or low temperature? Tell me.
Low temperature.
TCP forms at high temperature? relatively. Right?
Yes, sir.
So this one is the TCP and the first one is KCP. This one is slow forming, but there is no three-membered ring. So this would be more stable product here. This forms fast, but this would be more stable, right? Because sigma bond we have to break, so slightly higher temperature required here, hence it is TCP.
So there should be one more carbon in the product. also.
One more, yes. Got it? So like this, we'll write down the product in this one, reaction on carbonyl compound. Okay, not very much important. Generally in advanced, this kind of question they ask. But yes, you should know that carbon intermediate forms and we'll get this. Understood? Okay. There's two more example on the same reaction we'll see. I want you to write down the product directly. Okay, you don't have to write down the mechanism because all these reactions, the mechanism is not important. Okay, suppose we have H here and it is allowed to react with CH2 and N2 and we heat this. One of the product is what? At this double bond, so that would be CH3C and we get oxygen on the top. With CH2 we'll get this ring and here we have H. Okay, this is a CH2 from this diazomethane. Another one is CH3 C double bond O and we insert CH2 between this carbon and this hydrogen. Here simply you need to apply the migratory aptitude. Hydrogen is a better migrator. Then we have pH and then we have R group, right? Methyl, ethyl, whatever it is. If methyl, ethyl you have to compare, right? Then better electron donating groups are better migrator. Okay, this is what just you need to keep in mind. Where you have to insert that CH2 for that migratory aptitude you can apply. Like for example, could you tell me what is the product we get here in this one, pH C double bond O CH3, and when we heat this with CH2CO, product is KCP is the triple three-membered ring, that is PHC OCH2 C, and this CH3 will be as it is. TCP will be the insertion of CH2 between the more migratory aptitude the group has and C double bond O. This is the product we get. Correct? One more example you see. HC double bond O with the same reagent. The three-membered ring is this. And the other group is H CH2 C double bond O and this. So wherever the insertion of CH2 we have, that is TCP, more stable one.
The ring one, the 3-membered ring one, is KCP, less stable one. Understood this? So fine, we have last 2 reactions in this. We'll finish that, and few reactions of aromatic chemistry we'll see next class, and we'll start with a new chapter again. Okay guys, so revise all these reactions is very important. Thank you so much. Take care. Bye.
Thank you, sir.
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 Thank you.